So in this video, we're going to be illustrating Mohr Circle, and in this particular example, we're going to use Mohr Circle to determine the normal and shear stress components on the inclined plane shown in red on this element. And if you take a close look at this element, this is a fairly simple element. We need to identify, when we start the solution, we need to identify what we know. We know that sigma x is a positive 500 kPa because it's causing a tensile effect. Sigma y is 0. Tau xy is also 0. So pretty simplistic element. And of course, the angle that we're interested in that's defining the inclined plane is 30 degrees. And based on, even though I didn't explicitly draw an arrow here of which way it's rotating, it's pretty clear that it is rotating in a counterclockwise fashion just by the orientation of that dashed plane there, that dashed line. So these are our preliminary values that were given. So if you remember, and if you look back in your notes from the previous generic Mohr Circle video, the first thing we actually did was we computed the center of the Mohr Circle. Okay, so we're going to say compute the circle center, and that's a point. Okay, that's a point. It's sigma average, comma 0. So in our case, sigma average is just, it's sigma x plus sigma y over 2. So it's 500 kPa plus 0 over 2. And of course, that gives us the point 250 kPa, comma 0. So that's the center of the circle. So we're going to need to use that here in a minute. The next thing we did was we defined a point that we called point A in the previous background video. So we're going to write this out, define point A. Okay, and in order to define point A, what we did was we looked at the element as it originally is, and we put on our local and global axes, which looked like this. And on this element, we showed the applied stresses. Again, that's 500 kPa, 500 kPa. And when we defined point A, we said take theta equals 0. So defining point A, all we're doing is we're just specifying that the global axes correspond with the local axes. So I'm going to say y equals y prime and x equals x prime. Okay, so these are our first definition of the point. Now, one thing I want to make clear, we don't want to confuse theta equals 0 with this theta equals 30 degrees. Remember, the theta equals 30 degrees, that is just an inclined plane of interest, and it doesn't matter what the inclined plane of interest is when you're drawing the Mohr Circle. You draw the Mohr Circle the same way no matter what your inclined plane of interest is. This 30 degrees could be 40, 50, 60, 222.3 degrees, whatever. It could be anything. That doesn't have anything to do with how you actually sketch the circle in terms of defining a point A and a point G. So just kind of keep that in the back of your mind. So when we define point A, remember point A is defined by the coordinates, the general coordinates, sigma x prime, comma, tau x prime, y prime. Well, if your global coordinates and your local coordinates are corresponding with one another, then sigma x prime is just sigma x, and tau x prime y prime is just tau xy. And for those numerical values, we have a positive 500 kPa and then 0 for the shear stress value, tau xy. No surprise there. Okay, so after we've defined point A, the next thing we define is a point that in the previous video we called point G. And in order to define point G, we rotated the local axes 90 degrees counterclockwise. I'm going to say CC for counterclockwise, not to be confused with your classmate CC. So CC here is counterclockwise as opposed to CC Rakowski. That's my joke for this video. I hope you're all laughing and enjoying it. So in defining point G, we're going to rotate the local axes, but we're not changing anything else. So let's sketch this point right here. So I'm going to put on my global axes again. Here's my global X and Y, nothing different. And then I'm going to put on my stress values that are still in the same spot they were before, 500 kPa and 500 kPa. But what's different now? Well, the local axes have been rotated, okay? So in a different color in green, I'm going to show how my local axes have rotated 90 degrees counterclockwise. So what is pointing up right here? What local axis is now corresponding to the global y-axis? Well, that would be the local x prime axis. And where would the local y prime axis be? Well, the local y prime axis is now pointing to the left. Okay, so it's pointing along the line of the negative global x-axis. So here's y prime right here. All right, so now let's define point G with respect to these local axes. So point G, again, we use the generic sigma x prime, tau x prime, y prime, but we're looking with respect to the local axes, right? Remember these primes right here indicate local axes. So when I do this, what is my sigma x prime value according to these local axes? Well, look at what's happening at your local x prime axis. Nothing, right? So this would be a value of 0. And then what about the tau x prime y prime value? So that would be what should be the shear stress along this plane, which happens to be 0. Remember, it's a very simple problem. So this is the point 0, 0. So that's our point G. All right, so we have 3 points now that are important. We have the center of the circle, 250, 0 kPa. We have point A, which is 500, 0 kPa, and then we've got point G, which is 0, 0. So now we're ready to draw our circle because we have enough information to sketch it. So I'm going to try to sketch this very nicely. So my vertical axis is my tau axis. My horizontal axis is my sigma axis. And again, you need to put units on these because these are stress values and they carry units. So we have one important point over here. This was point G. And then we have the point A. Let's say point A is somewhere over here. Okay. And point A, again, was a value of 500, 0, and G was 0, 0. And then in the center, we have the center point that we know. Let's say that's probably right about here, and that's 250, okay? And remember that line AG that we defined in our previous video, that is the diametric line of the Mohr circle. That means it's defining the diameter of the Mohr circle, okay? So now we can sketch the circle passing through A and G, all right? So I'm gonna hopefully try to draw this circle very nicely. Surprisingly, this went okay. I'm going to try to fix the top half of this circle. Okay. That's probably as good as it's going to get in terms of my artwork. Okay, there we go. So there's our circle sketched, not beautifully, but decently. and this is it. So some things to note, even though the problem didn't directly ask for it, some things to note is that A and G both are the principal stresses, right? A actually happens to define the major principal stress, and G happens to define the minor principal stress. That's not always going to happen. It just so happens in this case because this is a very simply loaded element. But that's not what the problem was asking for. What the problem was really asking for is what are the stresses on the inclined plane at 30 degrees. Okay, so here's what you do. You start along the horizontal radial line from the center to point A. Okay, so here's what we're going to do. We're going to begin with the radial line defined by the center and point A. So that's this line right here. Okay, and then what we do is we rotate in the same direction as our desired plane, but with an angle of 2 theta. So in our case, this would be 2 theta equals 60 degrees, rotating counterclockwise. So what we're going to do is we're going to rotate up about right here, 60 degrees. And we kind of discussed this in the previous video as well about how the orientation in the element is some angle, and then the corresponding orientation on the circle is 2 times that angle. So I'm going to use a different color here, and I'm going to project a vertical line down here. So guess what we're looking for? The problem said, what are the normal and shear stress components on the inclined plane? So on the Mohr circle, that's actually this point right here. This is the value of sigma x prime and tau x prime y prime desired. Okay, so let's calculate this. Okay, well, check it out. You got a right triangle right here. All you got to do is use that right triangle. Do you know what the radius is? Well, I hope you know what the radius is. You know the diameter is 500 kPa. So of course the radius is 250 kPa. I mean, just look at it. Look at your diametric line that we use to define point A and point G. The radius is 250. I mean, you can look at it right here as 500 minus 250, and then it's a circle. So this right here, this line right here is still the radius. Okay, so all we need to do is use some right triangle trigonometry. And again, we're interested in this value right here. This is sigma x prime that we're interested in. And then this vertical component is tau x prime y prime that we're interested in. So I'm literally operating in this right triangle. So sigma x prime is going to be 250 kPa. That's the radius. I'll back that up and make sure we're clear on that. Radius times cosine of 60 degrees. So 250 kPa times cosine of 60 degrees should get me 125 kPa. And then tau x prime y prime is the radial value times the sine of 60 degrees. So that's 250 kPa times the sine of 60 degrees. And when I punch that through, I get about 217 kPa, and those are your answers. So the thing to keep in mind is in this problem, we actually were not asked or interested in the principal stresses. We were asked and we were interested in the stress components at a plane oriented at 30 degrees on the element, which means it's 2 times that on the Mohr circle. That's where we got the 60 degrees, okay? And if we wanted to get the principal stresses, we could, but in this problem, we were not asked for that. So make sure you read your directions carefully and answer the questions that are being asked of you.